Today we will discuss double integration method determining the deflection and slope of elastic beam. As an overview, I will give you concepts of double integration, then the procedure for analysis and examples. Once the moment is expressed as a function of the position x, then successive integrations of the equation d squared v over dx squared is equal to m over ei will yield the beam's slope. That is, tangent theta is equal to dv over dx, which is equal to the integral of m over ei dx. Take note that the tangent theta is approximately equal to theta because the deflection is very small. An equation of the elastic curve is v is equal to f of x, which is the double integral of m over ei dx. So that's why we call it the double integration method. And take note that for its integration, it is necessary to introduce a constant of integration. Since we will integrate it twice, so there will be two constants of integration. And then you can solve for the constants to obtain a unique solution for a particular problem. Recall that if the loading on the beam is discontinuous, that is, it consists of a series of several distributed and concentrated loads, then several functions must be written for the internal moment. Take note, it's valid within the region between the discontinuities. So you have to be careful in making the equation and for the region of that internal moment equation. First, for an example, we can consider the beam shown below. The internal moment in regions AB, that is for the uniform loading. BC, there is no loading. And CD, again, there is no loading. Must be written in terms of the three coordinates. That's x1, x2, and x3. So, like for example, for x1, it is only valid within A to B. x2 is valid from B to C, and x3 valid from C to D. So one of these functions are integrated through the application of the equation d squared v over dx squared is equal to m over ai. And the constants of integration determine the functions will give the slope and deflection of the elastic curve for its region of the beam for which they are valid. And with these functions, we can then determine the slope and deflection at any point along the beam. So in general, we can actually derive an equation for the whole beam for the slope and deflection. When applying the equation, it is important to use the proper sign of the bending moment M. As established earlier, we use positive deflection V as upward, and the positive slope angle theta will also be measured counterclockwise from x-axis. So in this case, the positive increases dx and dv in x and v create an increase d theta that is counterclockwise. Also, since the slope angle theta will be very small, its value in radians can be determined directly from theta is approximately equal to tangent theta is equal to dv over dx. So the sign convention is very important, especially for the bending moment M. If you look at this figure, the left hand side, if the moment will create clockwise direction, then that would be positive. And also on the right hand side, if it will create counterclockwise rotation, that would become positive. So with the deflections which is upward, which is taken as positive, and the slope angle theta measured counterclockwise is also positive. The constants of integration are determined by evaluating the functions for slope or displacement at a particular point on the beam where the value of the function is known. Normally that is located at the supports or at the portion or regions where the slope is zero. And of course, we call these values as the boundary conditions. If, like for example, for this beam, we have the support A, we assume that at support A, since this is a hand support, so it restricts the translation, the X and the Y direction. So there will be no deflection at point A at x1 is equal to 0. Also, the same is true with C. Vertical displacement is restrained, so there will be no vertical displacement at point C. So at the length of the beam, that is x1 is equal to L, then the displacement at point C, that is vertical displacement, is equal to 0. That's how you determine the boundary conditions. Also, at the peak support, the slope and displacements are both 0 because we need to to restrain the horizontal, vertical, and the moment. So if a single x coordinate cannot be used to express the equation for both the beam's slope or the elastic curve, then continuity condition must be used to evaluate some of the integration constants. Consider the beam as shown. Here, the x sub 1 and x sub 2 coordinates are valid only within the regions AB and BC. Once the functions for the slope and deflections are obtained, they must give the same values for the slope and deflection at point B. That is x1 is equal to x2 is equal to the distance A, so that the elastic curve is physically continuous. Expressed mathematically, this requires that the angle of rotation at theta 1 is equal to theta 2 at the same distance A, and the displacement should be the same, B1 and B2 at the distance A. These equations can be used to determine two constants of integrations. For the procedure for the analysis, the following procedure provides a method for determining the slope and deflection of a beam or shaft using the method of double integration. It should be realized that this method is suitable only for elastic deflections for which the beam's slope is very small. Furthermore, the method considers only deflections due to bending. Additional deflection due to shear generally represents only a few percent of the bending deflection, and so it is usually neglected in engineering practice. For the elastic curve, we can draw the exaggerated view of the beam's elastic curve. Recall that points of zero slope and zero displacement occur at a peak support, and zero displacement occurs at pin and roller support. So this is very important. You have to remember this one. Establish the x and v coordinates axis. Again, you can just use x and y coordinate axis, or here x and v. The x-axis must be parallel to the undeflected beam and its origin at the left side of the beam with the positive direction to the right. If several discontinuous loads are present, establish x coordinates that are valid for each region of the beam between the discontinuities. In all cases, the associated positive v-axis should be directed upward. For the load or moment function, for its region in which there is an x coordinate, express the internal moment m as a function of x. Always assume that m acts in the positive direction when applying the equation of moment equilibrium to determine m is equal to a function of x. For the slope and elastic curve, you have to take note that the provided EI is constant. Apply the moment equation, EI d square v over dx square is equal to mx, which requires two integrations. For each integration, it is important to include the constant of integration. The constants are determined using the boundary conditions for the supports and the continuity conditions that apply to slope and displacement at points where two functions met. Once the integration constants are determined and substituted back into the slope and deflection equations, the slope and displacement at specific points on the elastic curve can be determined. The numerical values obtained can be checked graphically by comparing them with the sketch of the elastic curve. Positive values for slope are counterclockwise, and positive displacement is upward. Take note on this constants of integration. This is an indefinite integral. We have to do that one. Otherwise, be careful with the definite integral. That is, since you know the boundary conditions, you will just substitute it now. do not substitute it directly. Use a constant of integration so that it will we will be able to apply the boundary conditions later on. In general, the double integration method, the differential equation of the elastic curve is defined as d square y or dv over dx square, which is equal to m over ei. Here, y is the vertical displacement or deflection, x is the distance, horizontal distance from the origin towards the right. M is the moment equation, and take note actually in this equation we have the modulus of elasticity and the moment of inertia I. Before in our computations we never talk about EI, but here you need to understand that we need to know the properties of the material, the modulus of elasticity and the cross section of the material. Normally it is I. So if it is rectangular section with respect to the x, the moment of inertia is 1 over 12 bh cubed. So you need to know the section or the moment of inertia to be able to determine the deflection and the slope of the elastic curve. Here is an example. Use double integration method. Establish the equations for slope and deflection for the uniformly loaded beam. This is a simple beam with uniformly loaded load. Evaluate the deflection at midspan and the slope at support A. Assume EI is constant. So here we have a loading of W and the length of the beam is L. Uh, you need to compute the reaction, but since this is symmetrical, we can just take the resultant W times L divided by 2. That would be the reaction at both supports. That's WL over 2. So the right hand side diagram, we need to cut at a portion of the beam. Again, in determining the moment equation, you have to make a cut. Okay, method of section. You can cut, then you can just choose the left hand portion of the beam or the right hand portion. In this case, it's easier to use the left hand portion of the beam. So when we cut, we need to include the external forces and the internal forces and moment. In this particular diagram, we only need the moment. So the we did not necessarily put the share, but actually there is also a share for it to be in equilibrium. But in this particular problem, uh, we are only concerned with the moment. So if we have to sum up moment at the cut portion, and clockwise will moment is positive, so the reaction WL over 2 will create clockwise rotation, that is positive, times x. So that's why M is equal to WLX over 2 minus the resultant of this uniformly distributed load, that's W times x, times the distance or of the resultant from the point where we sum up the moment, that's x over 2. So here we were able to establish the equation of the moment, that is W Lx over 2 minus Wx times x over 2. So in this case, since we establish a rectangular coordinate system with the origin at support A, the slope is negative at point A because as you can see, the beam will rotate this way, concave upward. So there will the rotation at A will be clockwise. That would be negative. And of course, since this is the structure is symmetrical, so with the loading, so the maximum deflection will occur at the midspan where the slope is 0, and positive slope at point B because it's counterclockwise. If we consider a pre-body of the beam cut by a vertical section located at distance x from the origin at A, we can write the internal moment at the section as we have derived earlier. M is equal to WLX over 2 minus WX squared over 2. If we substitute it to the equation that we have, that's d square y over dx is equal to m over ei. Before substituting, we can just rearrange this equation, multiply EI to the left hand side of the equation, that would become EI d square y over dx square is equal to n. Of course, it's not necessary that we have to cross multiply it, but for this particular problem, it would be easier if we just remove it from the moment equation. So that the equation will become EI d square y over dx square is equal to WLX over 2 minus WX square over 2. Then we can now integrate this equation twice with respect to the distance x. Of course, this will yield this following equation. I will not discuss how integration process is done. I believe you already understand that one in your calculus, so we can just directly integrate the equation and add the constants of integration, that is C1. Another integration will result to EIY, which has added another constant of integration, that is C2. This equation 7 has two coefficients or constants of integration, that's C1 and C2. And to evaluate these constants of integration at C1 and C2, we can use the boundary conditions at supports A and B. At support A, x is equal to 0, and as we have noticed, since that's a hand support, so the deflection is 0. If we substitute x is 0 and y is 0 at equation 7, then C2 is equal to 0. Another boundary is at support B. If x is equal to the total span, that is L, and y is equal to 0, we can substitute again this boundary condition at equation 7. And solving for C1 will result to minus WL cube over 24. Substituting the values of C1 and C2 to that equation, the two equations, equation 6 and 7, will give us these equations. This is a general equation for this particular simply supported beam with uniformly distributed loading. But we are interested at the maximum deflection located at the midspan. So if we have to substitute x is equal to L over 2, it will give us y is equal to 5 over 384 times WL to the fourth over EI. Actually, for this particular type or case of the beam, you need to memorize this one. It will really help. Later on, you will realize that the the maximum moment or the maximum deflection for this particular case of beam is simply a function of W L to the power 4 over EI times 5 over 384. Also, compute the slope at support A by substituting x is equal to 0 to determine the slope at support A. That is theta A is equal to dy over dx. Again, it should be negative because it's counter or it's a clockwise slope. So that's minus WL cube over 24 EI. Take note at the L, the power of L in deflection, it's L to the 4, and for the theta, that's L to the power 3. Another example is a cantilever beam. We need to establish the equations for slope and deflection by double integration method. That is if we have a concentrated load applied at the end point. Also, determine the magnitude of the slope theta b, that is the slope at the pre-end, and the deflection delta b at pre-end. Assume that EI is constant. Look at this diagram. Since this is a fixed support, so there will be no deflection at support A. So the elastic curve should be tangent to this support, and then it goes down slowly, that one. So the distance from point B to this one is the deflection, that is delta B. But the rotation of this beam taken from this one, from the horizontal line to the rotation, is what we call theta B, the slope at point B. So again, we need to establish the moment, and it would be easier if we have to cut the beam at this portion and choose the right portion of the beam. Assuming the x-axis is from A, the distance here should be L minus x. So the moment here should be equal to P times L minus X. And it should be negative because it will create a clockwise moment on the right hand side. It should be counterclockwise to be positive. So if we have to substitute this moment equation to the equation d square y over dx square is equal to m over ei, we can integrate this twice to establish the slope and deflection. So here again we have two constants of integration, and to evaluate the constants of integration we can use the boundary conditions imposed by the fixed support at A. That is, when x is equal to 0, the deflection is y is equal to 0. So if we have to substitute it in equation 17, and then C2 is 0. And also at x is equal to 0, since it's a fixed support, there will be no slope at support A. So that's why at x is equal to 0, the slope dy dx is equal to 0. If we have to substitute this boundary condition in equation 16, then C1 is also equal to 0. The final equations for the theta or dy dx is equal to minus plx over ai plus px square over 2 ei. Also, y is equal to minus plx square over 2 ei plus px cube over 6 ei. And to establish the unknown, the theta b and delta b, we substitute x is equal to L to compute theta b is equal to minus PL square over 2 EI, and delta b is equal to minus PL cube over 3 EI. Again, it's important that you have to memorize these results because these are special cases of beams loaded with special loading, that is concentrated load. So that's PL cube over 3 EI and PL square over 2 EI. Also, we have another example. Although it seems like this is not a beam, but actually this is still a type of simply supported beam. This simply supported floor joist is subjected to uniform design loading of 4 kilonewton per meter. Determine the maximum deflection of the joist, and take note that EI is constant. Since the joist is symmetrical and the loading is symmetrical, we expect that the maximum deflection will occur at the midspan. So here we assume that hence at the left support and roller at the right support, so there will be no displacements at both supports. So here we can just cut at any section, and assuming that at left portion of or the left support will the X starts. So here we have the internal moments. Force, we write all the forces and the moments. We have the shear V and the moment. The moment M is simply equal to 20 kilonewton times X minus 4 times x over 2. That's 20x minus 2x squared. So that if we have to substitute this equation to the equation that we have, that's d square v over dx squared is equal to m over ei, we will have this equation, and integrating it twice will give us these two equations with constants of integration. Again, you can just substitute the boundary conditions. At x is equal to 0, there will be no displacement, so C2 is 0. And at x is equal to 10, that is on the other side of the beam, the deflection is also 0. So that C1 is equal to minus 166.7. The equation of the elastic curve is therefore given. EIV is equal to 3.333 x cubed minus 0.1667 x to the fourth minus 166.7 x. At x is equal to 5, that is at the middle, we initially say it will give the maximum deflection. At maximum deflection, the slope should be 0. So here, dv dx is equal to 0 at x is equal to 5. If we have to substitute that to the equation above, then the maximum deflection can be computed, which is equal to minus 521 over AI. Another example, a cantilever beam subjected to a couple moment m sub o at its end. We would like to determine the equation of the elastic curve, and assuming EI is constant. Again, here the beam, there will be no shear. Actually, it's only a couple. So assuming that x starts from the left, we can just cut the beam anywhere and choose the left hand portion of the beam. So here the moment is simply equal to m sub o all throughout the length of the beam. Substituting m is equal to m sub o to the equation and integrating twice will give us this equation 2 and equation 3. And substituting the boundary conditions, the slope dv over dx is equal to 0 at x is equal to 0, and v is equal to 0 at x is equal to 0. Then c1 is equal to c2 is equal to 0. Both integration constants are 0. So that theta in terms of couple is equal to m sub o x over ei. And the deflection is mo x squared over 2 ei. The maximum slope and displacement will occur at the pre-end at x is equal to L, for which by substituting x is equal to L to the equations above, then the maximum slope theta A is m sub OL over AI, and v sub A is MOL squared over 2 EI. Again, it doesn't hurt if you memorize these values for that particular case of a beam and the loading. It's very important because we will be using that again and again in the coming discussion. Also, we have a beam that is subjected to a load P at its end. Determine the displacement at that end C, and assuming EI is constant. So here we only have a concentrated load at point C, and the beam is assumed to deflect in this way, that is concave downward. Take note again that at support A there will be no deflection, and at support B. So if we have to cut our, or to, if we develop our moment equation, we can just use two coordinates because there will be changes of the loading or discontinuity. From A to B there will be no loading, so that's one region. B to C there is no loading, so that's second region. Assuming our origin will start at support A, then we will have x1 for the segment AB and x2 for the segment BC. So we have to cut or make a cut at both of the segments. For segment AB, we have the first diagram. That's the moment is equal to minus P over 2. And then for the second cut at BC, we have the moment minus positive P over 2 times x1. That's the first segment. The second segment, positive P over 2 times x2 minus 3P over 2 times x2 minus 2a, and that would be the bending moment at that particular segment. So here are the moment functions that I am saying, but of course m1 is only applicable from 0 to 2a, and m2 is only applicable from m2a to 3a. Here are the elastic and the slope curves for the two segments. So expect that there will be two sets of equations because we have two segments. And by applying the boundary conditions, you will be able to determine the constants of integrations. And of course, you can just use algebra to solve these equations so that after determining V2, you can now compute the displacement at C as determined by setting x sub 2 is equal to 3a, which we get VC is equal to minus P a over a to the power 3 over AI. I think that's all for the double integration method. I think I have given you enough examples, and again, it will really take time if you will just be looking at the equations. It's very important that you really have to try yourself so that you will really see how double integration works. Thank you for